Hey guys, welcome back to NextWave News. Today, we're talking about a discovery that's turning our understanding of physics on its head. Scientists have managed to superheat gold to nearly 19,000 Kelvin, over 14 times its melting point, without it melting. That's right. A metal we usually associate with jewelry and electronics just rewrote the rules of thermodynamics. Under normal conditions, when you heat a solid beyond a certain point, it melts. It's what we expect, and it's what decades of theory have taught us. But researchers wanted to know what happens if you heat something so quickly that it doesn't have time to melt. To test this, scientists used a powerful laser pulse, just 45 quadrillionths of a second long, to rapidly heat an ultra-thin piece of gold foil. Right after that, they hit the same piece of gold with an intense X-ray pulse that allowed them to directly measure how fast the atoms were vibrating. Basically, how hot the gold had become internally. The result was shocking. The gold remained solid, even at temperatures close to 19,000 Kelvin. That's more than twice the surface temperature of the sun and far above gold's usual melting point of around 1,300 Kelvin. This kind of heating, extreme and nearly instantaneous, creates what's known as warm dense matter, a state found deep inside planets, in the hearts of stars, and during fusion reactions. It's a regime that's been extremely difficult to study until now. What makes this breakthrough so impressive is that it's the first time scientists have directly measured the temperature of matter in this extreme state using a non-guesswork method. Instead of relying on models or estimates, they track the actual motion of atoms in real time, giving them hard, reliable data. But the implications go beyond gold. This experiment proves that the so-called entropy catastrophe, a theoretical point where solids are supposed to fall apart under extreme heat, is not as absolute as we once thought. If you heat something fast enough, you can push it into regimes we didn't believe were physically possible for a solid to survive. And this new method could soon be used on other materials like iron or aluminum, elements that make up the interiors of planets like Earth and Jupiter. By observing how these elements behave under similar conditions, scientists can simulate and better understand planetary cores or even fusion reactors, where matter is exposed to incredible pressures and temperatures. There's also a huge upside for fusion research. In laser-driven fusion, where energy is blasted into a target to create controlled nuclear reactions, knowing the exact internal temperature is vital. This new technique offers a much more precise way to gather that data, helping engineers build better fusion systems in the race toward clean, limitless energy. This is more than a gold experiment. It's a door opening into the physics of extremes, where matter doesn't behave the way the textbooks say it should. A realm where solids stay solid when they absolutely shouldn't. A realm where our models and assumptions are being challenged by real-time data. If you found this breakthrough as fascinating as we did, make sure to like this video, hit that notification bell, and subscribe to NextWave News so you're always in the loop when the next wave of science hits. Thanks for watching, and we'll see you next time.